Welcome everyone to the third in the four-part series on computational Bayesian methods by Jose Ramirez and Fang Chen. I just want to mention, you're free to enter questions into the question box, but we'll probably defer most of the questions to the end. We might take a couple in between, but for the most part, we'll handle the questions at the end. Okay, Jose and Fang, in your court.
Okay, thank you.
Got it. We're back. Good morning, good afternoon, and I'm afraid to say good evening, but if you're someone on a Friday night watching this webinar, hats off to you. We're impressed. I want to thank you all for the nice discussion we had last week in terms of the questions. Shows that you're paying attention and you're interested in this, so that's good motivation for us. As Stan said, we're gonna defer some of that. And I know there's some questions that are more technical. I just want to remind you that our idea for these webinars is just to give you a tour of what is possible. It's not comprehensive, but some of the applications of Bayesian methods within CMC, so sort of to whet your appetite, so to speak. One thing I will mention that feel free to get in touch with the wonderful Mahalia, the IQ, in terms of if you may want. I know there's some people could not attend all of the webinars, and there's some people that may want this repeated. We may consider doing this again next year. Also, we may consider, if you find a topic from here that is interesting, we may just give one webinar, 2 hours on a particular topic where we can spend more time in the technical details and answer more questions. So this is what we've been doing, a tour of things. And as we've been doing, as you remember, we have some data sets, we make some distributional assumptions. As by now, you know that the assumption of normality is one of my pet peeves. Then we talk about the choice and visualization of priors. We have shown you some diagrams of that, some pictures of what the prior densities look like. And then mostly we're concentrating on MCMC. We'll show you a little bit of BGLIMM code today. And then we've also been talking about the interpretation of this and some of the technical details of this. So we're going to continue with it, setting acceptance criteria. And we've been covering a lot of examples on that. And we're going to get into comparability. And part 2 has been with what we call diffuse or non-informative priors. We're going to start using the prior knowledge. If we have time, we'll start today. If not, that will be next Friday. So sorry, just going to move forward because this is a bit. Okay, take 2. So this is where we are. So continuing with the setting acceptance criteria, we show you some examples with simulated data for the normal. We also talked about count data, either Poisson or negative binomial. The last example that we did last Friday had to do with viability data, which is a quantity between 0 and 1. And we show you the difference between just forgetting about the data itself and just using the normal, using a logic transform because that normalizes the data, and using a more appropriate distribution for a data between 0 and 1, which is the beta. So we compare that. So next, we're going to show you one of my favorite examples here, which is limit of detection data. And that's because of 2 reasons. One, because we have that data in CMC a lot, and because a lot of times people don't know what to do with that data, that's sensor data. And then we're going to show you another example how to use this methodology if you have some variance component, but the goal is not the variance component themselves, but to set a tolerance bound in a variance component scenario, which translates into having a statistical model. So far we've just been generating bounds with a simple model, but now in the last example, we'll show you a variance component model. So as I was saying, the limit of detection data, the LOD, that's left sensor data, and we're going to be showing you how to generate an upper bound for that limit of detection data using a log logistic distribution. So this has to do with TOC, the total organic carbon. When you're looking at the parts washer, so a lot of you may be familiar with that. And these sensors have a limit of detection. So the limit of detection, LOD, induces left censoring. You have why there's a question mark, because we do know that the number exists, but we don't know what it is. All we know is that it's less or equal that limit of detection. In other words, Y is detected, but it's not known. And this situation is different from when we have truncation, okay? And we'll talk a little more about that. So we have censoring then, and censoring, we have mentioned this before, censoring is very common in reliability engineering. A lot of reliability engineering deals with right censoring, left censoring, interval censoring. And I have mentioned this before, that in those cases, the normal distribution is not that normal because we're dealing with physical quantities that most of the time are positive, okay? And here, this is not an exception. So we need an upper bound for this situation. It's a positive quantity, as just mentioned. Normal distribution is not going to do a good job at approximating this data. We have several choices: Weibull, log normal, logistic, or log logistic. And the log logistic has the same relationship that the log normal has with the normal. If you take the log of the log logistic, that is the logistic distribution, and that is the equation of the PDF. And I'm highlighting there, we're highlighting where alpha and beta have to be. Alpha has to be a quantity in the real line, and beta has to be a positive quantity. That's important because our prior choices will have to reflect this choice for the parameters, because remember, we're going to put priors on the parameters of this distribution. We're going to be putting a prior on alpha and a prior on beta. Okay, so this is the data. The limit of detection is 0.05 ppmc. That stands for parts per million carbon. Okay, and you know, this is a huge data set because we have 1,047 observations. I always joke with people when they talk about big data, and I tell them, if I get 100 observations, that's a big data set for me. And I know that you may be smiling too, because if you're in CMC, our data sets are not that big. So we always deal with small data sets, but this is a large one. However, out of those 1,047 observations, 788 of them are left sensor, meaning 788 of them, we know that they exist, they were detected, but they're all less or equal than 0.05 ppmc. We're going to approximate this data using a logistic distribution, and this is a log logistic probability plot. Most of you probably know and use probability plots as a way of assessing if a distribution is a good approximation to your data. This is a plot out of PROC reliability in SAS, and PROC reliability, the name says it all, is a great tool. If you just want to generate probability plots, it's a great tool, but it also does all the fitting from the frequentist point of view if you have sensor data. So you can see there that this log logistic distribution approximates the data well, and it tells you we have 259 on-sensor observations. There's 0 right sensor, there are 788 left sensor, and there's 0 interval sensor. So you can see that when we talk about censoring, there are 3 types: left, right, or interval. And we'll show how we take that into account when we write out the likelihood. And again, we need an upper bound. As far as I know, there's no frequentist approach for this. There is an approximation for the log logistic distribution. Again, an approximation to get a tolerance bound for the log logistic. But if you have censoring, that approximation breaks down. Okay. So we're going to use, as we've been doing, diffuse priors on alpha and beta, and we're going to generate a posterior distribution from alpha and beta. And by now, you know that we can just take those parameters, plug them into the quantile function, and get the posterior distribution for the quantiles. And then from there, we're just going to get the 95th percentile of that posterior distribution. And we want here a 99.865% limit, meaning if we're thinking of coverage, we want a 99.865 coverage, which is kind of like what we call a 3 sigma equivalent coverage. Again, the technique is the same that we've been using. Put priors on the parameters of the likelihood, generate the posterior distributions of parameters, plug those into the quantile function. And yes, SAS does have a quantile function, you see that, and what the first parameter in there is the distribution, and the log logistic is one of them. So this is a little bit of the diffuse priors that we mentioned before, and the reference to the end. And the diffuse priors on alpha and beta. Remember that alpha can take any value in the real line, so that's the prior. And again, this is what sometimes non-informative priors are called flat priors. And you can see this goes from minus e to the 15 to e to the 15. And this is where Fang may be twitching, because this makes absolutely no sense, to have a prior like this, like that. Yeah.
Is there a reason for the for the e to the 15s and the e to the 15s is essentially the largest value that a lot of systems allowed, maybe the 32-bit number is allowed. So this is just an indication of a uniform prior over the entire range of what we consider to be negative infinity and positive infinity, because realistically, if you do estimate a parameter come from, a return value of 1 e to the e to the power of 16, you would be very surprised, and you wouldn't know what to do.
Exactly. And this is where where I agree with Fang that this seems a little silly. I mean, this is non-informative, but we do have information of this on these parameters. If you had this data on a regular basis and you had fitted either logistic model, log logistic, or y, well, you have a sense for where that alpha parameter lies. So that is what generates some informative priors. But in any case, this is a picture of that non-informative prior, diffuse priors. Remember that the parameter beta for the log logistic can take any value on the positive real line from 0 to infinity. Again, 0 to, as Fang said, 1 to the 15. So one thing that we want to talk about is the data. So the data has to have a specific structure in order to be able to use it, either with PROC reliability or with MCMC. So what we need to do is define 2 new variables. So notice in this data set, there is a TOC variable here, and that has a value, the 0.05, 0.05, 0.076, the 0.5s are the LOD. That's our data. What we need to create is 2 variables. I'm calling it LTOC for the left sensory and RTOC for the right sensory. So the left sensory variable has the value of missing if it's left sensor, and the RTOC has the value, the actual value of TOC. Okay, so you can see the first observation, which is left sensor, that's the LOD of 0.05 ppmc, has a missing value for the LOTC, and the actual value, the 0.05 at the ROTC. So that means that we know that it's less or equal than 0.5, but we don't know what it is. That is this interval. So what we're doing is transforming our sensor data into interval sensor. So this is an interval. You know what the upper bound is, but you do not know what the lower bound is. That is the left sensor. If it's right sensor, and we do not have any observations like that, it's the opposite. Then if you have right sensor data, you know what the lower bound is, and that's the TOC, and then the upper bound is missing. And if you have interval censoring, then in this case, no censoring means the LOTC is the same as the ROTC, which is this. So this value had a TOC of 0.054, which is greater than the LOD. And for that, we put that as 054 and 054. So that tells the procedure that that value is exact, okay? The upper bound and the lower bound are the same. Now, having that data set that way, then we can proceed with the SAS code. So let's look at this. The first thing that we look at is this. So that instruction is important, the missing AC.
Oh, sorry, I was talking, but I muted. I didn't realize I was unmuting myself.
Yourself.
Yeah, I was talking. So I was going to explain what this AC stands for. All cases. PROC MCMC handles missing value just by treating what's missing value. Is slightly different from a lot of procedures, because by default it treats the missing response as a parameter, and it draws samples from the missing values by default. And so in the procedure, it has different ways of differentiating what type of missing value it handles by default and what missing values it would lead to a deleting of the observation. So in this particular case, because the censoring indicator is missing and that observation should be kept, you want to use the option called missing equal to AC. Just means MCMC is just going to keep every observations, and you will the user will be responsible in handling how they are dealt with as case arises. So that's why there's a missing equal to AC.
Again, so this is very important. So if you're dealing with sensor data, PROC MCMC, you need that. And as Frank said, we're going to show you how we tell MCMC how we're dealing with the sensor data. So the next things are the priors.
Yeah, the prior, just the general prior of zero. Zero, again, just to remind people, is a log of 1, and it's a uniform on the real axis. So general 0 represents a uniform distribution on the anti-axis, and as a prior on beta is a uniform prior on the half of the axis. So it's 0 and with lower equal to 0. So
and that's why we have the lower bound, no?
Yeah, that's the lower bound. That's the beta. Then beta is lower bound, and then the next portion is compute additional calculation, compute which is the mean and the mode and median that are functions of the alpha and beta parameter from the log logistic model. They are functions of the posterior, so they themselves become a distribution we can estimate.
Yeah. We know. And you can see that, some of you may wonder, you see mean and mean 2. Those are exactly, they give you the same value, but there are 2 ways of writing the mean for a log logistic. I just wanted to show off and just put it there, just to make the case that if you know the equations, you can put them right in there. Again, and this is one of the beautiful things about the Bayesian approach, is that once you have the posteriors for alpha and beta, you can pass them into any formula, and then you get the posterior for that. And the other piece, if you're not too familiar with SAS, you can see here constant pi. That means that SAS is going to use pi.
Pi is 3.14. Right.
Yeah, exactly. With just that
internal value. That's
internal value. So you don't have to type it exactly. So that's in case you don't know. And then.
Oh, I want to add one more thing. This code, the mean mode and the sigma, all these evaluation can be either done in PROC MCMC, or you can do it afterwards in data step. So I want people to know that sometimes you don't need necessarily rerun a program. If you have written your MCMC program, and when you write the program, you forgot to compute the quantity of interest, you don't need to rerun the entire program to get the same thing. But we put it in here because we feel it makes the whole presentation more readable, because we are doing the simulation and then we are infer on the functions of the parameters.
Exactly. And I'm glad you mentioned that, because if you're paying attention, you won't see a quantile function in this piece of code. And the
Yes.
quantile was calculated after the fact in a data step. So sometimes actually it saves you a little bit of time, depending on how big your problem is, to do these calculations in a data step, because it would be way faster. So the last thing we have here is the likelihood. And this is a little more complicated. I'm gonna let Fang explain this, and this is how we tell MCMC how to deal with censoring.
Yeah, so this is the one of the traditional way of doing censoring, because censoring is considered to be integral missing values that you integral over a range. So it depends on if you are left censoring, right censoring, or interval censoring. It is the area in the curve that's what it counts. So you can see that if there's no censoring, which is the first if statement, then the density itself is a logistic density, but we do log PDF because we work on the log scale of the PDF.
And Fang,
yes,
this log PDF, I'm sorry, is unique to MCMC, no?
No, this log PDF are data step functions.
Yeah.
The log PDF, log CDF, and log SDFs are all data step functions.
But they're very handy in MCMC.
They're very handy, yeah. And MCMC has its own log density functions, which is slightly different LPDF that actually has truncation information in there. But in here, we are using the data step LPDF, LCDF, and LSDF functions in there. So moving on, the next line is the left censoring. Left censoring is equivalent to the CDF, so it's the so yeah, it's a cumulative function up to that point, up to that.
So essentially, as you were saying, we're integrating the PDF between infinity or zero, depending what the lower bound is for the support of that distribution, and the RPOC. And I think this is important because when people deal with LOD data, sometimes just people get rid of that data, or sometimes people just set it to the LOD. But from the statistical point of view, what we're doing is partitioning that CDF, that integral, into pieces. So we don't know what the left censor value is. So you go from minus infinity to that value, and then you have a piece for the exact data, which is that, and then the rest. Sorry, I just wanted to make that.
Right. That's exactly what censoring is, and you know what the bound is, and you know that it happens cumulatively from the left end of the supportive distribution to that point. So the contribution of that particular censoring is that to that, and similarly to the right censor is the other side, is the log of SDF. So to the right hand side. So
and what is SDF again?
SDF is cumulative density function. SDF is a right tail survival density function, is to the
which is 1 minus the CDF. No?
1 minus the CDF to that point, but it's the right tail. Think about the right tail.
Exactly, which is the right tail. So you don't even have to write 1 minus. You can, again, SAS has those functions. So if you want the right tail of your distribution of that integral, then it's the log.
Right.
And then finally.
And finally is if you have interval censoring, which we don't have in this case, but if we did, then the interval censoring is the difference between the CDF and the SDF, the difference between, and you have to take the log. So in this case, it becomes slightly computationally tricky because CDF and SDF function themselves is not in general as stable as the log CDF and the log SDF, since just more stable on log. But in this case, you can't use log CDF and log SDF directly because the log of difference is not the difference between logs, and so you have to compute the CDF function call and SDF function call prior taking the log. So that's why. And this is called the marginal approach. A marginal approach just means we have an integral function and we know exactly what's the area under the curve in these situations. But if we don't, then the Bayesian also has a missing data approach, which you would have to use the truncation lower and truncation upper and treating that as a missing. So we sample enough missing value in that right region, and we Monte Carlo over, would have the same effect as direct use of log PDF, log SDF, and log system. So,
yeah, and that's the difference between censoring and truncation. For censoring, as in this case, the LOD, the data was detected. We know it exists, but it's below 0.05. Truncation means that there is no data. We truncated the data at 0.05, and that doesn't exist. So now we have the code. We can let PROC MCMC run, and we get the results. So you have the results here, and you can see the estimate for alpha is -34473, for beta is 0.455, and then you have the mean, mode, and median, and sigma coming from those formulas that we put in there. We added here at the bottom, that's from PROC reliability. As I said, PROC reliability can fit a log logistic. The data set has to have that format. And what do you notice? What do you notice? You're getting the same parameters. So this is another example. If you use the diffuse priors, your Bayesian results tend to be what the likelihood gives you. So in this case, if we use now the posteriors for alpha and beta and plug them into the quantile function, we get the upper bound of 0.55 ppm carbon. So
yeah, I also want to add that we think that this the closeness of the two estimates is because in this particular case, the posterior distribution of alpha and beta are normal-like, but that's not always the case. So even Bayesian in this particular case gets very similar to MLE when normal approximation breaks down in cases of different type of data, then you don't necessarily get exactly the same answer.
Yeah, and it's a good point. So yeah, exactly. Don't expect it all the time. Right. But here, I'm putting this level of comfort. Remember, one of the things that we're trying is to lift the veil of suspicion on this technique. But you can see that if you know how to specify the problem, you know how to specify the data set, and now you know how to specify the data set for sensor data, then you can generate an upper bound with sensor data. This is just a case of left censoring. You can do this with right censoring, with interval censoring, and there's some a little more complicated problems where you have all types of censoring. But as you saw the likelihood in the PROC MCMC code, you can handle them all in just one pass. So now we're going to deal with variance components. Okay, so now we're going to go into a more complicated model. Before it was just a model of the mean, we just needed a lower and upper bound. So we have data, and this comes from the paper by Wolfinger in 1998, and Fang and I were talking the other day, it's almost a quarter of a century. And this paper is great. If you don't know who he is, he works for SAS, and he was the brain behind PROC Mix. I think yeah. I mentioned that before. And he also was the brain behind the macro, the GLIMM Mix macro before we have PROC GLIMM Mix. So he's still at SAS. But in 1998, he wrote this paper in Technometrics about how to derive tolerance bounds for variance component models. Guess what? Using Bayesian techniques. So these techniques go way back. And we're going to be, some of these techniques that we're using go back to him, and we really like this paper. So this data comes from Bengal, 1992, 5 batches, 5 measurements per batch. And if you're in CMC, you're like, yeah, that could be our data. It could be assays or 5 measurements per assays. So you can see the 5 batches there and the little distributions of 5 measurements per batch. So this is one case where you have balanced data. And we'll see that some of the priors that we're going to use are for balanced data, but this can be done if you have unbalanced data too. So this is a standard variance component model. You have your data, Yij, and you have a mean, and then you have a component, A sub I, that represents the batch-to-batch variation, and then the residual, the epsilon ij, that represents the within batch variation. So this is coming from the 5 batches, and this is coming from the 5 observations within the batch. Nothing different there. Hopefully, most of you are familiar with mixed models, and you can fit that with PROC Mix or PROC GLIMM Mix. But now what we want is we want a lower tolerance bound in this quantity, okay? because we want to make sure that the tensile strength is more than something. And we talk about these acceptance criteria that are used for that, to set a specification, to set limits for our data. In this case, the strength has to be more than something. So in the paper, they wanted a 95% confident, 90% coverage, okay? So the frequentist approach, there's a paper by Hoffman and Krinkle where they propose an approach where you can get bounds and intervals for variance component models with only one variance component. So I must say that this is kind of like an approximation, like a Satterwhite approximation, because what the paper does is they use the effective sample size to adjust the variance components. But it works well. We use it internally at Amgen to generate variance component when we have these scenarios. You know, we have batch
just
and
to add
observation with the batch. Yes.
a point. That effective sample size is not the same as effect sample size in the Markov chain convergence.
Correct. Yes. Well, let's call it ineffective. You know, for those of you maybe familiar with that correction with ineffective in the spirit of the Satterwhite approximation for the degrees of freedom. Okay. Now, you did not know this. PROC mix can handle Bayesian, and actually, when Ross Wolfinger wrote this paper in 1998, that's what he used. He used PROC mix. So you probably didn't know that back in 1998, PROC mix had the capability of running Bayesian analysis.
Yeah, I need to explain a bit on how the philosophy behind PROC mix and the Bayesian computation. So the PROC mix by default treats the model as a frequentist optimization problem. So the optimization problem in frequentist, the model parameters are the fixed effects beta, the variance components, and the residual, if there's any residual. The random effects themselves are considered to be latent parameter, and what PROC mix is finding the formula to have them integrate out and maximizing the remaining parameter. So it's not strictly doing MCMC per se, and when it does the prior statement, Wolfinger, they found a new way for variance component. You can generate from this marginal posterior distribution of the variance component parameter without the random effects, use a very clever approximation. And that's why they put the prior statement into it. So it's not the strict MCMC on all parameter approach like the BGLIMM does. It handles variance components in that particular way. So just give people a background.
Yeah, thank you for the background. Thank you. Now you mentioned BGLIMM.
Yeah, the BGLIMM now is a different thing. BGLIMM does not integrate out the random effects. So BGLIMM does as many random effects as they are, and it just does straight up Markov chain Monte Carlo sampling. It samples the fixed effects, the random effects, the G side covariance matrix, the R side covariance matrix, and then come around do the whole thing through Monte Carlo to get the marginal posterior of the parameter of interest. So,
and you can specify the priors, no?
And you can specify the prior, yes. On the model statement, it's the prior, scale prior is for the residual variance, and on the random statement is for the covariance, it's for the G side parameter of the parameter. They can be higher dimension. They don't have to be univariate.
Got it. So this is how you write the random effects model in PROC mix. You have your model, and then you have the random batch. So the cuff prior, that will be for the A sub I in the model, the batch to batch variation, and the one in the model statement, which is a residual, will be for the within batch variation. And then there's
fixed effects. There is a default. There is intercept. We know that's why there's not a intercept in this.
Yeah. So that's one thing that BGLIMM has. It has default for priors when you specify the model. So you don't have to specify the priors per se, no?
And you can use if BGLIMM for non-informative prior is what you would want to use, then BGLIMM does what you want. But if you want to switch to these non-standard prior, for example, a box and tau prior that has a joint prior on the G side and the residual side of variance parameter, then you would need to use PROC MCMC.
And that's what we're going to show you.
That's what
But if you use these approaches, so if you use the Hoffman and Kringle approach, you get 332. If you use the mix, you get 338. BGLIMM gives you about the same number, 338, and PROC MCMC gives you about 338. So you can see how the three procedures in SAS under the non-informative prior gives you about the same lower bound, and that agrees with the number in Wolfinger's paper. Now the box TR, we're going to show you that prior is not informative, but it's a joint prior. Again, it's joint because you can see the formula combines the sigma E is the residual, that's the within batch variation.
Yeah, this is also known as a Jeffreys prior on the joint parameter of the sigma alpha and the sigma epsilon, and it has an n in it, and then at the end is the number of observations per batch, and that's why you need to have a balanced batch for it.
Yes, exactly.
And just so that people don't get confused, in this particular variance component hierarchical model, if you use a Jeffreys prior on the variance component itself, that will lead to an improper posterior. So if the Jeffreys prior is on sigma alpha square, then you would get a improper posterior, and you don't want to use that at all. But the Jeffreys prior on sigma square, sigma alpha square, and sigma epsilon square, that Jeffreys prior lead to proper posterior, but the condition is that you need to have balanced data. So
yes, yeah. And so this is an old prior back from 1970.
Yeah,
from
this is
Professor
73,
Box
way before 50 years ago.
Yeah. And that's from the book on Bayesian statistics by Professor Box. And I was mentioned this before several times that in the old days, in the past century, the frequentists like Professor Box, which was very pragmatic, they had no issues using either a frequentist approach or a Bayesian approach. So now we have a joint prior. We go to MCMC.
MCMC, right. And then now the MCMC, this is how you specify joint prior, and that's a form of the that's the formula, and you take the log. Always remember to take the log of that formula, and then you see that the prior specification on sigma epsilon and the sigma alpha is in single line because they represent, the box tail represents a joint prior on both parameters. And why is joint prior on both parameters? Because both parameters appear in the density variation prior specification of the prior. Yeah. And you don't want to use two prior statements, one for sigma epsilon E and sigma epsilon A, then we'll get you the wrong answer. Yeah. And then the lower equal to 0 is the option that applies to both parameters. So both S sigma 2 epsilon and sigma 2 alpha both need to be positive with it.
And again, S2A here is the batch to batch, and S2E is the
yes. So the random statement is on the random effects, and then now it's the gamma. And we know the prior. So the random statements works to specify what the random effects distribution is. It says it's a normal prior with mean 0 and a variance sigma square alpha, which is fine. It's similar as a prior, but because there's many random effects, so there's more than one gamma in this particular case. And how do you specify the random? Being random, it's a subject equal to batch. Okay, so when you do subject equal to batch and you look at the data, and in the data, the batch goes from 1, 1, 1, and 2, 2, 2, and 3, 3, 3, etc. For data that have batch equal to 1, all observations in that subdata set have gamma 1 as a random effects. That's being sorted out internally by PROC MCMC. So however, it doesn't matter however many unique values you have in batch variable, PROC MCMC will generate a random effect for each of that unique value in the data set and match to the correct observation in the data. So that's how the random statement works. You don't need to specify. You don't need to know how many random levels they are, how many batches that you have in advance. PROC MCMC will sort this all out.
And this is great because it has, for those of you who know SAS, this has the same flavor as the random statement in PROC Mix and GLIMM Mix. And this is also, you'll see it later on, this is very handy when you deal with hierarchical models. In the first webinar, I mentioned that as a frequentist, you know, we talk about variance component models. Bayesians talk about hierarchical models. They see a variance component as a hierarchical model. Right. Then we have the likelihood.
The likelihood is just the intercept mod parameter mu over intercept plus the random effects gamma, and the residual is sigma SE.
Yeah, so this is a within batch variation. And then, as you've seen before, this is a quantile function. And one thing I want to mention, someone asked this last week. Notice I have the sum of the variance components because I want the total variation on my Y's.
Right.
Yeah, so that's this S2A, which is the batch to batch, plus S2E, which is the within batch. So, and you can put that anywhere there. You can calculate any sum of variance components. Once you have S2A and S2E, then as you've seen before, you can write any equation of those. You can do it here. You can do it in a data step after the fact using the posterior data set.
Right, and just let me add one more thing to that, is that this is a prediction from the marginal quantile, because it just like Jose says, it accounts for both variability, and that's why it uses mu. So that's the marginal prediction is what you want in a quantile estimation.
Exactly, and that ties in with the next. So we're going to talk about two-sided tolerance intervals. Someone asked a question last Friday about, you know, what about two-sided intervals? What about getting the QL and the QU, the lower and the upper, and just using those? And before we answer that, just to refresh your memory and tolerance interval, and if you don't know, there are mainly two types of tolerance intervals. One is called the beta content tolerance interval, and that is essentially what we've been using, confidence and content. The beta is the content, the coverage. Like in this example, we want a 95% confidence, 90% lower bound. Or we've been using 95% confidence, 99.865 to mimic a 3 sigma coverage. This is a future performance of the product, okay? And they're based on the quantiles of the assumed probability distribution. The other type is the beta expectation. You can think in terms of practicalities, the probable range of operation is like a prediction interval for one future observation. The B content is for the population. The beta expectation is for one future observation. They tend to be narrower than the beta content interval, okay? So now, in terms of the tolerance intervals, that idea of just using the QL and QU separately, we cannot do that because the posterior correlation of the QL and QU is not one. If you think about a tolerance interval, when you say I want 90% coverage, going back again to the integral that we're talking about with the censoring, what you want is that the coverage of that distribution, if you integrate it between QL and QU, you want that to be 0.90. So you, in essence, what you have is an integral equation where you have to find QL and QU. So they're dependent on each other. However, as Frank just mentioned, the QL and QU give samples of the bivariate posterior density. But what we need is one-dimensional interval. We can, no, using the bivariate is not that practical. And this is, again, where this paper is very nice, because Wolfinger, not only they found a clever way, as Frank said, of using PROC Mix to do this, but he suggests a way of getting a one-dimensional two-sided tolerance interval. So what he says is, okay, compute the QL and compute the QU. Don't use the coverage. Use kind of like a Bonferroni type adjustment, okay? 1 plus the coverage over 2, 1 minus that, and then 1 plus the coverage over 2 for the upper. And then use a graphical method. So you're going to plot the QL and QU with the QL on the left axis, and then you use the line that goes through the center of that, and then you make sure that find the interval where the lower, the bottom right here, the area here, this is 5%, for example, if you want a 95% confidence interval. And this line here.
And the 5% just means you count 5% of the posterior sample draws.
Exactly, yeah. And it's this line with, and this is what makes that correlation. So QL now is minus Q times twice the posterior mean, okay? Or that's also the mean of the QL and QU, okay? So for the data at hand, the tensile strength data, that's what the QL versus QU looks like. In this case, QL is the quantile at 0.05, and the QU is the quantile at 0.95. Remember, the coverage is 90%, so 1 minus that is 10%, so we divide that equally, 5% on the left side, and then 5% on the right. That means 95%, okay? So that is what that density looks, bivariate density looks like. And again, this is, you get that from PROC MCMC, and you can put it in PROC SGplot, and you get that plot. Okay? And now, with a little bit of SAS magic using PROC IML to count these points here, you want 5% of the points of that distribution to be here. You can find that interval by making sure that you first define the line, and then going on the points on that line, you're going and calculating, you know, how many are there until you find that 5%. Again, that can be done with PROC IML, and the interval there is 337 to 434. So this gives you a way of getting a two-sided Bayesian tolerance interval with the right confidence and coverage. Okay. Now, Krishnamurthy and Matthew, they wrote a book in 2009 called Statistical Tolerance Regions. That's kind of like the standard book for all things tolerance bounds and intervals for different things. That's where you can find the approximation for gamma distributive values as the square root, as the cubic root. Now, what they say is that, yes, we're going to follow the Wolfinger's approach. It's a great approach. However, don't use the bottom right, but use the upper left to define the interval. So rather than having 5% at the bottom, what you want to do is have 95% in the upper left. Okay. So that's for 95%, as we said, you know, Wolfinger looks at 5% at the bottom, but Krishnamurthy looks at 95% on the upper. And that's what we got with Wolfinger, you know. But the problem with this is that you can see these dots here. You know, you have these points. Some points are where you have the point out here. These could be affected by these extreme intervals. So you may get something that tends to be more a beta expectation than a beta content. And this is what you get if you use the Krishnamurthy approach.
Right, and I mean, typically it's not a problem if the distribution have right tail, which is fine, and but often what happens is because the extreme value happens, the range of which does happen depends on the simulation. It's more prone to the simulation, and that would make the right lower bound estimates, interval estimate, to be somewhat of more of a variability than if you do the left upper bound.
Yeah, so we're going with Krishnamurthy and Matthew and using that. Again, those calculations and the plots were generated using with PROC IML. The beta expectation tolerance interval is just simply generating the predicted distribution and getting the quantiles. That's like a credible interval. Wolfinger has that in his paper in 1998. Martin Otava, sorry if I'm mispronouncing your name. I think he's at Jensen. He gave a presentation where essentially he talked about the Wolfinger beta content and the Krishnamurthy and stuff. And he said, you know, we're going to use this one, getting a credible interval in posterior predicted values. But that's the same as Wolfinger in 1998. Again, we really like that paper. So that is the posterior predicted distribution, okay? And the fringe down here, those are the data points. And this is something that in Bayesian you do. If you generate a posterior distribution, it's nice to have the data there to see how well it approximates the data after the fact. That's why it's called the predictive distribution, because they should represent the data in the future. And this is one of the things I was saying, that one of the things about being in the SAS environments that you can take the data out of PROC MCMC and create some nice graphs like that. So for the tensile data, the Wolfinger interval is 338, 430. The narrower, it's narrower than the beta content interval. And how do we get the predicted distribution, you may ask?
Yeah, this is just straight up from predicting the marginal distribution of the future response without the consideration of random effects by integrate out. So that's a formula. And so random normal, because it's a normal likelihood. We even sensor data, we're talking about normal data likelihood and the predicting on the mean, and with that sigma to A and sigma to epsilon.
Yeah, notice that this is exactly, this is the sum of variance component, because this is what we're going to see in the future, or
right.
or observations or measure values.
Right, without the batch. Yes,
yeah.
Without the batch, and then that's a distribution that you see, and you can see that encompassing all 5 batches of the data. That's all within between the, and that is what you expect to see. And based on that, the posterior predictive distribution enable you to say this is the range of tolerance. I mean the beta content. Right.
Exactly, and that's why that acts like a prediction interval. Okay. So that is the end of setting acceptance criteria. And before we move to comparability, we just wanted to give you a little MCMC interlude here. Just explain a little bit what that is. So MCMC stands for Markov Chain Monte Carlo, MCMC, Markov Chain Monte Carlo. And it's a combination, I know Fan will cringe at this, but it's a way of explaining this. It's a stochastic process plus simulation. So let's say that you want to calculate the posterior expectation. You need to calculate this integral, theta, and this is the posterior distribution, okay? You want to calculate that integral, okay? In general, you cannot do that analytically. Very few cases, remember I mentioned that, I did that when I was at the statistical lab. If you use normal priors for normal data, you conjugate and all that, you can probably work it out by hand. But in general, we cannot do that with complicated problems. So what we need to do is we need to approximate this integral by sampling from that conditional distribution. So how do we do that sampling? And that is where the Markov chain comes in. So we sample using a Markov chain that converges to the stationary distribution. And that is the beauty of this. And this is, I believe, is what has made so much difference in the way that we approach Bayesian techniques now. And the reason why, Fang developed PROC MCMC to take advantage of these things. So in essence, and Fang mentioned this before, there is a theorem that says if you have a Markov chain that has this characteristic, it's aperiodic, irreducible, and is positive recurrent, then this integral here can be approximated by this sum. This is an average. This is the sum of the function evaluated at the Markov chain and 1 to k, where k going to infinity. AS stands for almost surely, so it's a probability conversion. Okay, so this is the analog to the law of large numbers in the frequentist world, and this is what makes thinning unnecessary. And here we just want to thank Professor Ruggiero of the Catholic University in Rio de Janeiro, Brazil. Hopefully he's attending today, because he's the one who checked this math and make sure that these conditions are the right ones. Again, this is some heavy duty math, but there is some theoretical support for this, and we'll show you another example of why thinning is unnecessary. This again is from the SAS documentation. We put it here because it gives you a good explanation. You just have a sequence of random variables.
Yeah, the the Markov chain, the nice thing about Markov chain, what the problem it solves is that when you do the simulation, you don't need to sample directly from the stationary distribution. You just need to sample something that's sequentially stepping towards something that's what you want. And the sequential is the random variable theta1 all the way to theta k. They're dependent on each other. This was a revolutionary idea that simplified a lot of problems in that. And as long as you can think that it's a Markov chain taking small step or large step and traverse randomly through a joint parameter space, then the sample came out of it. It doesn't matter where it's going to go next. It depends on where it is now, what's going to go next. The correlation doesn't really impact the Monte Carlo estimate. Yeah. So that's what we're trying to get into.
And yeah, I like the last sentence there because, with all this mindfulness going on, the Markov chain, you can think of that as a mindful thing because it only depends on where it's now.
Right.
So that's that.
Yeah, that's how Markov chain, the idea of using a Markov chain in sampling what we want in the Bayesian computation.
Someone asked about Winbox last week, and we mentioned that is based on the Gibbs sampler, but these are all the sampling methods that are available to you in PROC MCMC.
Yeah, PROC MCMC has what they call, these are the general sampling algorithm. Well, it can sample from a distribution without knowing what the distribution needs to be. So there are variations of it, and some of them are fancier than others, like the Hamiltonian Monte Carlo later on is very elaborate sampling algorithm. But PROC MCMC has a collection of these algorithms for different situations.
And that's in the SAS documentation. We're not going to get into all that, but we just show you that you have all these different sampling algorithms to your disposal. If you're really a heavy-duty Bayesian and want to play with these things, you can do that. You can even define your own sampling algorithm. So let me show you a sample. This is the variance components data. On the left side is no thinning, on the right side within 100. Some of you may be hyperventilating right now because you see the autocorrelation plots looking that way, and you say, okay, I need to do thinning so my autocorrelation plot looks okay. So that's for the mu's. And then this will be at the top is the batch to batch variation with no thinning. Look at the autocorrelation. At the bottom is the within batch, a little better with no thinning. Now, if you go on the right side with the thinning at 100, or you start feeling better because, look, there's no autocorrelation, my data is good. And again, we just mentioned that this ergodic theorem or a version of that is what allows to say that thinning is not necessary. And I'll show you why. So here on the left are the results, the posterior summaries with no thinning, and on the right with thinning equals 100. Look at the numbers, 388. 0.3, 388.3, they're almost identical. Okay, they're almost identical. If you generate the lower tolerance bound for the Wolf Fingers data with no thinning, you get 338.017. But if you use thinning of 100, you get 337.995. So again, it's proof that thinning is not necessary. But this is just the numbers. So you may say, well, on average, things may be deceiving, but don't take our word for it. These are the posterior distributions. The red is no thinning. The blue is thinning equals 100. So you can see they're right on top of each other.
Yeah, so and this is the effect of Monte Carlo estimates. When you think about Monte Carlo estimates, you think that the order doesn't really matter. It's just an average of things. You don't really compute the Monte Carlo average by asking which sample comes first and which sample comes next. So in a way, that the disregarding of the sampling autocorrelation among the Monte Carlo sample doesn't impact the Monte Carlo estimates for this reason, because of this ergodic theorem.
Okay, so
it's 12 o'clock. Shall we take some questions?
Maybe there's one or two questions, we can
Yep.
take them. Stan?
Sure. Here's a question. Should one not add +1 for interval censoring?
Wait, what does that mean?
This was on the slide. I don't recall actually the number of the slide when when you were discussing the difference between censoring and truncation.
Oh,
Yeah, so censoring means that the data exists, but we don't know what the exact value is. Truncation means that there is no data below that number.
but the question had to do with
I don't know the
+1.
n+1, what the question refers to. So.
Okay, let's go on to the next one. On slide 54, where did the UTB come from?
Oh, the UTB, for that, we just use the quantile function. Remember, we have said that as long as you have the posterior distributions for the parameters, you can plug that into the quantile function. And SAS has a quantile function that we have shown you. The first parameter of the quantile function is the distribution in quotes. And SAS does support the log logistic. So you use quantile log logistic and you pass the alpha and the beta and the content that you want. So in that case, would be 90%, 0.9. And that gives you the posterior distribution for the quantiles. And in this case, we want an upper bound. And so we just get the 95th percentile of that distribution. So it's the same approach that we've been using that was introduced by Wolfinger in 1998. So then, and as Fang mentioned, you can do that inside the PROC MCMC, and we have shown that several times, or you can do it outside in a data step. Okay. So
okay,
now, yep. Now we're going to move into comparability, which is another activity that we do a lot in CMC from the International Conference on Harmonization, the Q5E. I'm highlighted the pre-change and post-change. So we're comparing two things. So a comparability exercise is generally comparing two things. You can think of pre and post, or you can have a biosimilar comparing that to a reference product. So we use that for lot release in accelerated stability. Some people may do comparisons of the pre and post change of the slopes, characterization methods. A lot of the stuff that is done, at least from the frequentist point of view, is the means comparison. Again, if you're in CMC, you're familiar with this and some of the techniques that we use. If we're doing method bridging, same idea. We're comparing method, a standard method with a new method, and we want to show that the new method is the same or better than the new, or it's going to give us similar results. So normally when we do a method bridging, we compare the means and we compare the precision of the methods. We may want to characterize the difference. We can estimate the bias, which is essentially the difference between the means, and we want to compare the precisions because if it's a measurement system that we're comparing with a new one, we want to make sure that it has the same precision or better. If you're doing biosimilars, so in biosimilars, we're comparing a biosimilar with a reference product. You may be making a biosimilar for an Amgen product, Neupogen, and you want to compare that. And the FDA has had some guidelines and guidances. Some of them have been withdrawn. But essentially, what we're comparing is two means, and we use the two one-sided t-test approach, or the TOES. And what you see there, and we'll see this graph again, is you compute a confidence interval for the difference in mean, a 95% confidence interval for the difference in mean, and you just want to show that that confidence interval is completely contained between plus or minus what we call an equivalence acceptance criteria. And that's normally derived from the reference product, okay? But this has some issues, and if you've been dealing with biosimilars, you know what they are. It's very rarely that the biosimilar and the reference are going to have similar variances, so you have the issue of unequal variances. The acceptance criteria that was proposed by the FDA will depend on the standard deviation of the reference product, but the test also depends on the reference product standard deviation. So there are issues there of double dipping, if you will, for this test. Rick Burdick when he was at Amgen, and I suggested using the effect size. And actually, Rick has, I mentioned this before, written a paper in 2017 that won the Stan Alten Award, and the Stan Alten is our moderator. So he was a very important person here. So there's an award in his name, and that paper also explains what some of the issues are in comparability. So what we propose from the Bayesian point of view is that rather than just looking at the means or variances, we're going to look at posterior distributions. So you can see a picture there of the posterior distributions, one for the reference product and one for the biosimilar. And you can see just by looking at the posterior distributions, you can see if the location is the same. You can see that one distribution is fatter than the other. So that tells you, well, it has more variation than the other. So there's a lot more things that you can do by looking at the posterior distributions. So this will be a 4-dimensional approach where we're going to look at the mean difference between the two, like they do with the 2 one-sided t-test. But we're also going to look at the variance ratio because we know that the variances may be different. So one of the things that we do, at least in the frequencies area, we look at the variance ratio. If you remember, you take the largest variance divided by the smallest, that normally is approximated by an F distribution. We're going to look at the effect size, as Rick and I recommended, and we're going to look at closeness of the distributions. And here, people may use a Kolmogorov-Smirnov, things like that, but we're going to use something called the total variation distance. And this is something that they use actually when they look at convergence of Markov chains. That total variation distance is used. Okay? So we're going to look at comparability. So we're going to look at a biosimilar. This is Sandoz EP 2006 versus Neupogen, and that's something that Amgen makes. So this was, I think, approved in 2015. And if you're familiar with biosimilars in the FDA, there's a rigorous process that you have to go through. And one of the things that you have to do is you have to demonstrate comparability. So this is the data that we're going to be looking at. Okay? So the green data is the US Neupogen. We have different formulas. We have US Neupogen and we have the EU, European Union Neupogen. In this exercise, we're going to be comparing the red data, which is the commercial EP 2006, to the green data, which is the US Neupogen, and the blue data, which is the clinical EP 2006 to the Neupogen. So there will be 2 comparisons. These are the summary statistics. So you can see the mean of the green data is 100.15 with a standard deviation of 1.5. The mean of the blue data here is 99.63, standard deviation of 189, and the mean of the red data is 97.23, standard deviation of 1.7. So you can take that data and generate a 90% confidence interval and see that it's contained in the plus or minus EAC. The plus or minus EAC, you take the standard deviation of the reference product, in this case, the US Neupogen, 1.51. You take that value and multiply by 1.5. That's what the FDA used to recommend. So you take 1.5 and multiply by 1.5, and you get your plus or minus acceptance criteria. So from the analysis that the FDA did, you can see that the clinical versus Neupogen, they're statistically equivalent, but for the commercial, they're not, okay? And you have the sample sizes. This was 11 versus 12. This was 6 versus 12. And you can see that the batch, the average for the commercial is 97. The average for the clinical is 99. So the clinical, on the average point, from the average point of view, is closer to the 100, to the US Neupogen. However, the FDA, let's go back. So let's show you more detail this comparison. So I mentioned that one thing you do is you compute the 90% confidence interval around the mean difference, and that is this dot here. This is the difference between the 100 minus the 99, okay? And this is the 90% confidence interval. Remember, this value here is 2.26. That's the standard deviation of the reference product, which is the US Neupogen, which was 1.51. You multiply that by 1.5 and you get this. And this interval is completely contained there. So you say, yeah, They're equivalent, and that's the conclusion that you saw in the previous slide. Here is what happens to the commercial. I just mentioned that the mean for the commercial was 97, and you can see that the mean is completely outside that. There's a piece of the interval that is inside the EAC, but the interval, the complete interval, has to be inside. So that's why in the previous slide you saw this one pass, this one failed. However, the FDA made a note there, and I'm showing that to you, that the reason these happen is because of manufacturing, and that can be solved doing some things in manufacturing, some control strategies, and that's what SAN does. They don't think that we're saying that, you know, if you get a batch from commercial, it's not good enough. So we're not implying that here, okay? But this is a good example because you had the same data, okay, or for biosimilar to Neupogen, where you fail and one passes and one fails. And this is what, you know, going to make it interesting for the Bayesian approach. So I'd say that Rick and I suggested using the effect size. This will be the test suggested by the FDA with the 1.5, the standard deviation of the reference product. What we're doing is just moving the standard deviation to this side to standardize its difference. And you think of this is an effect size. So essentially that is glasses effect size, the different types of effect sizes. But if you divide the difference in mean by the standard deviation of the reference product, that will be glasses effect size. So in essence, you'll be comparing that to the plus or minus 1.5 rather than incorporating that into the AAC, okay? Now, rather than using that, we can just go straight and use the t-statistics. The t-statistics is a signal to noise ratio because the signal is the difference in mean. If the populations are close, this numerator here should be close to 0, meaning no signal, okay? But it's a signal to noise ratio because in statistics, whenever you have a signal, then you have to divide that by the appropriate noise to make sure that this is, you know, if it's a signal, this signal is greater than the noise. The noise for this difference, as you know, is the variance of this population divided by the sample size plus the variance of that population divided by that sample size. So we can use that. Well, what's the problem of using the t-statistics? If the variants are not known, when we do not know the distribution under the null hypothesis, and that is called the Behrens-Fisher problem. That's called the Behrens-Fisher problem. And one of the things that people have done in the frequentist point of view with the N effective is use the Satterwhite degrees of freedom approximation. And all of you may remember that if you're using the t-test, when the variances are not equal, then you use an approximation to the t-test. And you may remember that one of the first things you do if you're doing a comparison of two means is to first check that if the variances are equal or not. Or you can use some type of fiducial inference like Fisher did to try to solve this problem. That's why this is called the Fisher, the Behrens-Fisher problem, because Fisher made reference to the Behrens distribution. But from the Bayesian point of view, we have no issue because as long as we have the posterior densities for that mean this variance and that variance, we can plug them in here, and guess what? We get the posterior distribution for the t-statistic. We can get the posterior distribution for the t-statistic the same way we've been getting the posterior for the quantiles or any other function of the parameters. So again, from the Bayesian point of view, we don't have the Behrens-Fisher problem, and that's why we're using the t-statistic itself rather than the traditional effect sizes. And this is what we call an effect size in quotes, okay? So this four-dimensional approach, so what we're going to be doing is we're going to look at the mean difference, and that's the bias. So we're going to look at the posterior distribution of the mean difference. Again, if the difference in mean is not too big, that posterior distribution should be centered around 0, okay? The variances, we're going to look at the variance ratio. Again, if the variances are similar, the variance ratio should be close to 1, and that distribution should be centered around 1. Notice that that distribution has a long tail, and as you remember, the variance ratio, the distribution that we normally use for that is the F distribution, okay? Here, we don't have to worry about if that is exactly the F. We're just working with the posterior distribution. That now you know by the ergodic theorem that this posterior distribution approximates the true distribution of that variance ratio. We're also going to look at the T ratio, that effect size, so we can look at that actual distribution of the t statistic. Okay, that will be the Behrens-Fisher problem, but we now know what the distribution is. And then this is the total variation distance. The total variation distance is looking at the maximum difference between the probabilities given by one distribution and the other. So we're going to assume the same distribution, and we're going to calculate the probabilities given the posterior distribution of the parameters, and we're going to look at the maximum difference. That's going to give us a sense of how close those distributions are. So that's how we're going to do the biosimilar comparison. So this is the MCMC code. These will be the priors that we're using on the means.
Sorry, I was talking and then I realized I muted myself again.
That's no problem.
Go ahead. I mean, just go ahead.
So so here we put in the priors on the means. Notice one thing, that if you're not too familiar with SAS coding, notice that we're using mu colon. That is a simplification rather than putting mu R and mu TP. You just put that, and that PROC MCMC knows that
it's all parameters. It's all symbols that start with mu, and you can just, it's a simplified way of writing it, writing the thing.
So now we have.
Then this is just calculating the mean and variance and effective size according to the formula that was seen as we showed in the previous slide.
So the effect size here is the mean difference divided by the square root of that variance. So that's
the two variances corrected by the corresponding sample size.
That's the t statistic.
Right. And then the total variation is a bit trickier because this is looping over the range of 81 range, and each of them computes a CDF normal differences in that. That's just the total variation calculation.
And in this calculation, what we're doing is we're looking at the reference distribution, and we're going to plus or minus 4 sigma. We want to compute probabilities along the range of the distribution. You can make it out to 5 sigma, 6 sigma, but plus or minus 4. So we're getting 40 points from minus 4 to 0, they get to 0, and then 40 points to the right of 0. That's why you have 81 in that array. And then there's a little switching here.
The switching here is just to switch to normal likelihood with 2 different mean and 2 different variance parameter, and then depends on what the source variable is. Then there will be 1 mean and 1 variance, and then the other will be a different mean and different variances.
And EPCL stands for the EP 2006 clinical. So if the data is coming from that piece, from the EP 2006 clinical, then it has the TP. And then if it comes from the Amgen data, that's the reference product.
Right. Yep.
And then that's the likelihood. So we have that, we can run it, and these are the posterior distributions with intervals. So one thing here I want to show, if you look at the data itself, you take the difference of the clinical data minus the Neurogen data, that value is minus 0.52. You notice this posterior distribution for the differences mean the mode of that distribution is 0.5132, very close to that. So you can see right here that that distribution is close to 0, meaning there's no difference in the mean. That shaded area there, that's a 95% high posterior density interval, goes from minus 2.07 to 104. It contains 0, okay? On this side, we have the ratio of variances. Notice that mode is close to 1. This interval also contains 1. So you can say, yeah, the variances are similar. Right here is the T ratio. Okay, the T ratio is about minus 0.7. Okay, and then the interval there goes from minus 2.6 to 135. And then on this side, this may be something new for you. This is the posterior distribution of the total variation distance, has a mode of 0.16, and the lower bound is 0.2. The reason we're pointing to the lower bound is that if the distributions were on top of each other, the maximal distance will be 0. Yeah. So the closest this distribution is to 0 is the closest the two CDFs are. Okay, and then here is the traditional analysis that we do with a 90% interval around the difference in means contained with that interval. Yeah. So now let's look at what happens with the commercial. Remember, the commercial had the mean completely outside the lower equivalent acceptance criteria. Notice again, if I look at the data, I mentioned that the commercial data, the mean was 97. If you take the difference with the Neupogen data, that's almost 3 units. Notice this posterior distribution for the difference in mean is 2.9. And you can see that interval does not contain 0. I mean, the interval ends here, 0 is here. So that aligns with this conclusion. In terms of the variances, that contains 1. So even though the commercial data has a shift, in terms of variation, it's the same as Neupogen. And I think, this also will support that conclusion that, with some process controls, you can move that average up. Now, if you look at the T ratio, your T ratio is minus 3.3. Now, we all have a sense for what the T ratio is. If you know that the T ratio is more than 2 or 2.5, you know that you already have a signal. So what this is telling me is that the signal is 3 times the noise, so 3.3 times the noise. And that's why I like to present the T ratio as a signal to noise ratio, because it has that interpretation. And now notice what happens to the total variation distance. Notice how this has shifted. And now the mode is 0.6 and the lower bound is 0.27. The lower bound for the other one was 0.2. But you can see this better if we superimpose the distributions. The blue one is the clinical, the red one is the commercial. So now you can see the picture. If you look at the variances, commercial and clinical compare well to Neupogen. If you look at this, again, this aligns with the biosimilar analysis that we did. The commercial has a lower mean than the Neupogen and a lower mean than their clinical data. You can see the T values here. This is 0.6 and this is minus 0.3. Again, the commercial data has a lower effect size or a bigger effect size in absolute value. And this for me is the interesting one. See, you see this is a distribution, how close the distributions are in terms of the total variation distance for the clinical, and this is for the commercial. You can see how it shifts. So this hopefully gives you a sense of how to use that measure, how to interpret that. So this is what we propose. You can see how rich this is in terms of information and in terms of looking at the different dimensions of comparability, not just a tolerance, a confidence interval in the difference in means. Okay, so that's the conclusion from this analysis. And again, all this is done just by getting the posterior distribution, the parameters, and then you plug in that into this. You remember we did all these calculations within MCMC, but as Fans said, we can do it in a data step outside MCMC. So now we're going to look a little bit at method bridging, okay? Because that, again, that's something that we do, and that's a comparison between a standard method or a new method, or you may have a method here in the US and you want to compare it to a method that you have in Europe, for example. Okay? So essentially, you have 2 approaches. I know some of you may do some more sophisticated things, but you can test for equivalence of means, okay? Again, along the same lines of the biosimilar. And you may want to characterize differences if you want to go in a little more in depth. You can estimate the bias, and you can compare the precision of the 2 methods. And we're suggesting you can take some of all those 4 elements, or you can take some of those elements for that. And we're going to use 3 out of those 4 here, just as an example. So VCD, some of you may deal with this. In biotech, one of the key measurements is the viable cell density, okay? Because that measures how well the cells are growing. I sometimes tell people the manufacturing reminds me of making beer. You have these big stainless steel tanks where these cells are growing, and we have to keep them happy with the right pH, the right temperature, and the right conditions for them to grow. So we want to make sure that they're growing, and VCD is one of those quantities related to that. So it's a critical parameter. These measurements, because cells are growing, are usually taken over time. And they tend to follow some type of exponential growth. I mean, that's simplifying things, but that's the trick. And the other thing at this VCD, and you'll see the data in a little bit, they're positive quantities, and sometimes they're large in orders of magnitude of e to the 5, e to the 6. So the normal distribution here is not a good approximation. So this is the data that we have. On the left, you have method A, that's the blue, okay? And we want to compare that to method B. Okay? And if you're doing this from the frequentist point of view, you can compare the means. If you're just looking at the box plot, you can look at the center line, which is a median. Yeah, that kind of level. And you can see the height of the box as a surrogate for the spread in your data. That's the interquartile range. That's the 75th minus the 25th percentiles. And height-wise, they look like the same. Yeah, there's some large numbers here. Yeah. So that is that. We can do that. However, I just mentioned in the previous slide that this data is usually taken over time. So this data was taken over 4 days to observe growth. So now you have that. That changes the picture a little bit, no? So this is time 0 when we started taking measurements. Then after 1 day, after 2 days, after 3 days, and after 4 days. So you can see a few things that as time goes by, the means go up as expected, but also the variation changes. So some of these high values that we saw here are coming from here. Yeah. So here we're collapsing over time, which is probably not a good idea if we want to do justice to this data, and if we want to capture the differences, not overall, but also day to day. Yeah. So what we want to do is we want to compare method A and B, but we want to take into account the exponential growth that you see there. So we want to look at the mean differences at the different time points. We want to compare the mean at time 0 for method A and method B, the mean at time 0 for method A and method B, mean at time 1. After 2 days, what happened to the mean, method A and B? And after 4 days, you can see that for method A, these numbers are higher than that. Same at day 3. So method A is a little higher. And there's also a increase in the variation, and that's known. I mean, the variation tends to increase because there's more action, there's more growth. So what we want to do when we do an analysis is to take into account the structure of the data and the situation at hand. We want to try to adapt to that as much as possible. So variation is increasing with time. So it's a positive quantity, and for VCD, for titer, we tend to use the log normal distribution. And here, this is out of PROC reliability. And in PROC reliability, again, it has some nice features. So on the top, this is method A, and this is method B. So you can generate a log normal probability plot for 2 populations, have them on top of each other, and compare. It's very nice. I know you can do this in other pieces of software, but just to show you. So here you can see, yeah, the log normal distribution is an okay approximation. Also, based on what we know, and having used this distribution for that, is kind of appropriate, quote unquote. So we're going to do an analysis where we're going to do comparisons between method A and B. We're going to take into account this exponential growth, so meaning we're going to be doing comparisons over time. We're going to make sure that we take into account that the variation is increasing with time, and we're also going to use a log normal distribution. So this is a little more comprehensive analysis than if you just compare method A and B. Again, this is one of those reasons why we're using this Bayesian method, because it's easy to incorporate all of these dimensions in the analysis. So this is the code, right? So in the code, and it has several pieces here, we're gonna have the model parameters. So alpha and beta are the model parameters for an exponential model. If you think of the exponential model alpha e to the beta. And we also going to be modeling the variation. We're going to do a log linear model on the variation, meaning that the variation in the data, the log of the variation is an intercept plus a slope.
This is I was going to not a whole lot I want to add with this. Just go ahead.
Yeah. So again, alpha is a starting BCD, and beta is the growth rate, and beta 0, this is the intercept, and beta 1. And then here, as we just showed you for the biosimilars, we're switching the parameters essentially. If the data comes from method A, so you have alpha A, beta A, B0A, B1A, meaning you have an exponential growth for method A, and you have a linear relationship for the log variance for method A. And if the data comes from method B, then you have different parameters. Okay, we're feeding separate models depending of the data coming from A and B. And that's what's going to allow us to make the comparisons. Again, as long as we have the posterior distributions for these parameters, we can plug them in any quantity. Yeah. And at the bottom, you can see the exponential growth model. Alpha times exponential beta times day. Day is the one that measures 0, 1, 2, 3, 4. And this is the growth rate. Again, here you can use any model that you think is appropriate for this. We're using the exponential model because a lot of people are familiar with that model and it does an okay job at modeling growth, but you can use any other type of model. There are tons of models to model BCD growth, so you can put it there. And the variance model, that's the exponential beta 0 plus beta 1, meaning the log of the variance is just a linear model.
And usually, if you do have different models that you want to consider, a way to compare the fitness of the model would be use DIC, which we are not covering here, but you can just think of a DIC deviance information criteria, a similar Bayesian concept similar to AIC and DIC that PROC MCMC produces. You can fit different model and compare using their value to get a sense of fit.
Yeah, that's good. Yeah, we have forgotten about to mention the DIC. That's one.
And another approach people do is what we had done in the last example is you can generate from the posterior predictive distribution of each model to see how they fit with the original data. That's another approach you can do.
And here you notice that we're using the log normal distribution. But here, this is interesting. Notice what goes into the log normal distribution. The mean of the log normal distribution is the exponential model, meaning the mean depends on the alpha and the beta, and the alpha and the beta depends on method A. If you have method A, you have alpha A, beta A. If you have method B, this will be alpha B and beta B. So the mean is modeled exponentially, and that's why, notice this, how flexible this is. You're putting the exponential model in the mean. We also have a model for the variance, and beta 0 and beta 1 also change depending on A or B, and then just plug that model into the likelihood. Again, that shows you the flexibility of the Bayesian approach and the flexibility of PROC MCMC. Hats off to Fang again for giving us a procedure like that. So notice that here we are modeling the data over time, both in the mean and the variance, and using a log normal. So all those things that we want to take into account are done in the code. Okay? Now, this is a little more elaborate because we want to compute means and mean differences and variance ratios. Okay. So what happens is we want to do this in the data scale. So if you go to Wikipedia and do a log normal distribution, you'll find this table. And yeah, go ahead, Fang.
Yeah, I was just going to say is that this is over five time points of 0, 1, 2, 3, 4, and that's why there's a repeat time because the covariance X the time change, the date changes. That's why the code looks a bit busy and intimidating, and you can probably, but we just want to give you a sense of all these computations on computing the mean and the variances are just simple data step calculation.
Yeah, exactly. The sophisticated programmers out there may be looking at this. Hey, you guys.
You can use the do loop and over array, but in essence, it's the same thing.
Yeah. So what we're doing here is going back to the data scale, because the data is being modeled by the log normal distribution. So we get a mean and a variance for the log normal. So if you want to go back, this is where the formulas are. So if mu is the mean of the log normal and sigma squared is the variance of the log normal, the mean in the data scale is the exponential of that mean of the log normal plus half the variance. And that is the formula here, but it's a little more complicated because remember, the mean for us is this exponential mole and the variance is a linear mole. So I'm putting the mean plus half the variance. And I'm doing that 5 times. We're doing that 5 times, as Fang said, because we have day 0, 1, 2, 3, 4. And if you want the variance, then that's the formula for the variance, a little more complicated. And those are the variants. So we're computing the variances for days 0, 1, 2, 3, 4, 5. And we're doing that for A and B. You see A and B. And then you take the difference. So the mean difference at day 0 is the mean for A at day 0 minus the mean for method B at day 0. So you do all those calculations. Again, you can do these calculations outside PROC MCMC. And these are some of the parameter estimates, the alphas and the betas. And you can see the alpha A, alpha B, and this is the starting VCD at day 0. And you can see the difference is 0.1. So that gives you a sense of how close those models are. This is the growth rate, 0.25, 0.26, similar growth rate measured by method A, method B, that's good. And then these are the parameters of the log linear model for the variance, minus 466, minus 44, the delta is 0.23. These are the slopes for that. This slope is a little higher for A and B. That's not a surprise because, we saw that method A tend to be a little higher than method B. So now we're going to look at some of the comparisons. And these you haven't seen, it's called a caterpillar plot. You may have seen the plot, but you can get it out of one of those autocall macros for PROC MCMC. And what you're looking at here is the dot represents the mean difference of time at day 0. And then there is an HPD, a 95% HPD interval around that. This is day 1, day 2, day 3, day 4. And you can see that the intervals get really wide, and that reflects the variation. And here you have the variance ratio. This will be the ratio of the variance of method A versus method B at day 0, day 1. And also this line is 1, again, because if the variances are similar, that should be close to 1. If the difference are close, if the means are close, then the difference should be close to 0. So you can see there that the means difference are all greater than 0, meaning method A is higher than method B, but most of the intervals contain 0. And for the variances, most of the intervals contain 1. So these will be part of that assessment of looking at this. So one of the things that got asked last time, I'm sorry, and this is the plot of the data again, just saying that you can see how A is the blue, B is the red. So you see A is a little higher. So that's why the difference in means we take in A minus B, those differences are positive, and they're mimicking this. But once you take into account the noise and all that, they're probably not that different. So the methods compare over days. One thing that got asked last time was how do we deal with multiplicity? And this is something that has I don't think there's quite a consensus here. Gelman may say that we don't need to do any type of adjustments for multiple comparisons because the priors may take care of that. And that is true if you're using a hierarchical model, and we are not doing that here. So one thing we try here is do a Monferroni type adjustment. We have 5 comparisons. If you use an alpha of 5 and you use a Bonferroni adjustment that will give you an alpha of 0.01. That means that rather than generating 95% confidence confidence, the frequentist in me came out. Rather than computing 95% credible intervals, now you compute a 99% credible interval. And now all these intervals contain 0. Okay, and then here we have a comparison. The blue ones are no adjustments, the red ones are adjustments. And we added the lower bound there so you can see. So you can see that for day 2, the lower bound of the unadjusted interval is 0.17, does not contain 0, but for the adjusted one is minus 0.343, so that does contain 0. So if you do a Bonferroni type adjustment, then all the intervals will contain 0, and you can claim, that yeah, the methods, both methods mimic what the cell growth is. They do similar things over the different days. However, these are separate comparisons, and that's why we use the T ratio, because the T ratio is the signal to noise ratio. It combines both the mean difference and the noise of that difference, the standard deviation of that. So you can compute that again with code using, that, but you're going to have a T ratio for day 1, day 0, day 1, day 2, day 3, and day 4. And these will be the posterior distributions of that. So the first one here, the light color one, is day 4, and the dark color one here is day 0. Okay. And we had added lines at plus or minus 2.5 because for in the frequentist approach, if you think about the T distribution, the critical value for a T distribution, at the 5% level, alpha level, the critical value for 5 or 6 degrees of freedom is about 2.5. Okay, so as long as your T ratio in absolute value is less or equal to 2.5, you will not declare a statistically significant difference. Okay, and that's why we put those lines there. So you can see that with the exception of day 0, most of the mass of those posterior distributions are within the plus or minus 2.5. And here are the percentage outside here. For day 0, you have 9%, then you have 2%, or 2%, 1.8, all that. So just day 0. But day 0, I wouldn't worry too much because in day 0, there's not a lot of growth. So what we're seeing there is the effect of, any tiny difference is magnified. So we don't worry too much about day 0. So this gives us another look at this comparison. And actually, as I say, it's a comparison that combines both the difference in means and the difference in standard deviations. So just closing up this session, and we're gonna handle some questions. You can see that all the examples we have shown you, you can handle many types of difference acceptance criteria situations, continuous count data, binary data, that was the variability data, sensor data with the TOC data, almost any type of distribution. We use the beta, the Poisson, the negative binomial, the log normal, the log logistic. We use a variance components model. We use a nonlinear model with an exponential growth. Direct estimation of any of those difference, direct estimation of the T ratio, for example, that's done very easily. The credible regions and the HPD regions have a more intuitive interpretation. And we're looking at comparability in terms of the posterior distribution. You just saw the comparisons of method A and B based on the posterior distribution. We tend to prefer that than just looking at the difference in means and standard deviation. And we gave you a multi-dimensional comparability assessment, the 4 panels there, the bias, the precision, the T ratio, and then the total variation, distance as a closeness to the CDF. And again, you can, for the last bullet, you can substitute other things that you can think of in terms of measuring how the 2 CDF are close. These are some of the reference that we're using, and there will be, when we you request the materials that will be there. And next week, we're going to be looking at historical information, prior knowledge. So we have time for questions now.
Okay, we have a few philosophical questions. Here's one of them. Slide 87, how do you define what is sufficiently close for the results to be comparable?
87.
Yes, so I imagine we can try to go back to that.
Page 87. I mean, I guess I would go with.
You're looking at this, yeah?
Yeah.
Okay. So
quantify with
yeah.
a probability. I mean, I guess a probability of, usually a probability of identical to be zero is zero because we're looking at a continuous distribution, but we can quantify a probability of within a range of zero of the two differences.
Yeah.
That's how I would go about it.
Yeah, so you can quantify like that. The way I'm looking at this data, I'm thinking if I look at the mean difference, okay, the null hypothesis of the mean difference is that it's zero. There is no difference between the mean. So I'm using my frequentist hat here, and I'm looking at that interval, that gray area, which is a 95% HPD. Okay, that interval contains zero. So I can sort of interpret that as zero as a likely value for that. And I can look at the mode of that distribution, and that is 0.51. You know, if I look at the one on the top right, that I know that the ratio is the variances are similar, that ratio should be 1. The F test in the frequentist point of view is testing that the ratio is 1 under the null versus it's not. Again, I can look at that interval, and that interval contains 1. Now, this one here, for me, and that's the one we just showed you for the method bridging, is more intuitive because we do have a feel for that. That's the T ratio, that's the T, or close to a T distribution. You know, we don't know what the beneficial is, but it looks like that. So we know at least that if I have 6 degrees of freedom, the critical value for a T is plus or minus 2.5, meaning that between plus or minus 2.5, I expect to have 95% of the distribution. So I can put the minus 2.5 and 2.5 here and see how that does, how much mass is contained in there. And as Fan was saying, we can calculate out of this posterior distribution how much of that mass is above 2.5 and how much is below 2.5. And that is sort of a kind of like the p-value, quote unquote. In a way, not quite, but it has that flavor, not fine.
Yeah, in a way it is to that, and you can always compute the posterior differences between of two densities, and it computes the density differences to be greater than zero or away from zero. So that's another way, but it's the same idea.
Yeah, and that's kind of like we're doing on the bottom right here. Okay, this is something new, and the idea is how close to zero is to zero, and by itself may not be that helpful, but if we look at the comparison, then you can really see that in terms of closeness, the clinical data is close to the biosimilar, to the reference product data than the commercial data. Okay,
Yeah,
because the
you
distance.
can compute the difference between two distributions as well. Yeah.
Yes, you can do that. I'm saying this is not quite the same, but you're looking at the maximum distance between the CDFs, you know. So that gives you a sense. So I will use this panel, you know, for comparisons like that, like we did with the method bridging that we had day 0 through day 4. This allows you to see that, and you can see, you know, this is a T ratio. So we have a feel for that. A T ratio of 0.67. You can say your signal is only 0.7 the noise. That's not a big deal. But here, for this comparison, the signal is 3.3 times the noise. So in terms of a signal to noise ratio, that's probably a likely signal. So that's how we would do that. Okay.
On slide 60, there is a third type of two-sided interval tail control based on Owen 1964 instead of center control. This is useful, for example, in calculating lower confidence bound for CPK process capability. Is there a Bayesian equivalent?
Oh, you're talking about how we define the beta content for that?
Yeah, slide 60.
Yes, I'm going there. Yes, yes, there is a way. We haven't talked about that here. We just mentioned, that essentially there are two types right here. Yeah. Yes, so there are different ways of controlling that content. This is the beta content is kind of in the center of that integral equation, and it's kind of like the approach of using the quantiles. But yes, you can do that as long as you can specify. As you may have seen, one thing that we're doing is translating this mathematical problem into some code for MCMC. So if we can make that translation between and I'm going to use the word equation because when we're doing these calculations, there's some equations behind the scenes to do this, or some reasoning behind. Like this one, we're looking at quantiles for specific colors. Then we can translate that into what we're going to do with PROC MCMC. Is how we use this posterior distribution. But that's a little more elaborate. But in practice, in our experience, these are some of the two other intervals that we use the most. Now, going back to your PPK, CPK, and that is very interesting because there are a lot of papers written about approximations to a confidence intervals for CPK. And actually, SAS has four or five different approximations to that, okay? Here, what we will do is just go and get the posterior distribution for the CPK and work with that directly. We know that the CPK distribution, the CPK is a bias estimator of the actual CPK. And people don't talk much about this, but the required sample size to get a good estimate for that is about 50, But with the Bayesian approach, you can get the posterior distribution for the CPK and then do things with that. So hopefully that may help answer partially this question.
Thank you, Jose. If we have scientifically driven acceptance criteria and not SD-based, we can use them too, right? Is the question. This is for comparability.
Correct. This is not to replace that. Anything that is scientifically based, we use that. One of the things that we show though is you can use, if you have that, you can use these to see how good you're meeting that. In part one, when we were talking about acceptance criteria, we mentioned airlet levels, and there's certain ppm for that are set by the EPA. You can collect some samples, you can get an upper bound, tolerance upper bound for that, and compare that to that limit set by the EPA. And if that number is less, then you have some statistical support that you're going to meet it, and so that's how you can use that. So yes, no, we're not replacing that, but you can use these to compare to that. A lot of times you may not have the limits, and what happens is, and we did mention this too in the first webinar, you use this as a starting point just to give the subject matter expert, the scientist or the engineer, to give him that ability to say, okay, I can start at this point, and then I can bring the science and engineering that I know, and then I can come up with subject matter expert-based limit. Yeah.
For the VCD method, bridging comparability, were the batches samples tested by both methods? Shouldn't we consider a paired analysis for that?
Yes, we can include that here. It wasn't done, but in this case, the batches were not. But if the batches are tested, if the same batch is tested using the different methods, then yes, we need to bring that information into the model. It's just how we specify the model, and we can do that. As you have seen, mentioned that in the previous question, as long as you can translate the math into the code, then that's no problem. So you're thinking more of a pair t-test, so to speak. Yeah.
Right.
But that will change your estimate of noise for the mean difference. That's it boils down to that. So in that signal to noise ratio, but you still have a signal to noise ratio to look at the mean difference. Yes. Good point. Thank you.
Here's a question. How do you explain to upper management the choice between 9590 versus 9599?
You're talking about in terms of confidence or the coverage?
Or both. I mean, it's the same confidence the person is asking, but the coverage is what's changing.
Yeah, so that has to do, in my experience, with how much you want to cover for, what claim do we want to make? That it boils down to that. So I will ask them, what claim do we want to make? What claim we want to make based on this data? This data is going to support, and this analysis is going to support a claim. So if we go with 95% coverage, we're going to have a limit that is, let's say, plus or minus 2. If we're going to use a 99% coverage, meaning we're going to go wider, that's going to be plus or minus 3. So the claim that we're going to make is in the future, if everything remains the same, if our process is stable from the point of view of statistical control, meaning predictable. If my process is predictable, then I expect 95% of the population to be between plus or minus 2, or 99% between plus or minus 3. The other dimension to that is, how will the agencies take that number? Sometimes if you go to them with a plus or minus 3, since they have knowledge of this, plus they have information about other companies, they may say, that limit is too wide. So that it boils down to the claim we want to make, and also what's out there and how the agency is going to take that. But normally people tend to use 99, even 99.85, 865, because it's sort of the usual plus or minus 3 sigma. People are used to the rule of thumb with a normal distribution between plus or minus 1 sigma, you get about 68%, plus or minus 2 sigma is 95%, and plus or minus 3 sigma, you have most of the population. So the reason people use plus or minus 3 sigma is because they want to make a claim for most of the stuff that we're going to make in the future. You don't want to say, 5% is not going to be good. So again, those will be some of the discussions with management, but framing in terms of the claim that they're willing to make.
I think we're running out of time. I want to apologize to those whose questions could not be answered today, but I encourage them to follow up individually, and maybe we'll have time next week to address some of these.
Thank you all.
Yeah, thank you very much. Thank you.
And have a great weekend.
Yep. Have a good weekend.
Okay. Bye.
Yeah, bye.
Bye.